Hello, so we are looking at 15 Part A on the MAC 2311 review for Exam 1, Summer 2014. Okay, so Part A says, explain why the intermediate value theorem does or does not guarantee a solution on the given equation in the specified interval. So for 15A, we're looking at that one. Okay, so let's talk about intermediate value theorem a little bit. So intermediate value theorem, all it's saying is that if you have some function on some graph and it goes from up here where the y values are positive to down here where your y values are negative, it's pretty hard not to hit 0, right? So from positive to negative, you gotta hit 0, and just the same for negative to positive, you gotta hit 0. Now you're probably thinking, I can think of a couple cases where that doesn't happen, right? Like a discontinuity, when you have a jump. I did not hit 0, right? I teleported almost. I went from positive directly down to negative. Or an asymptote would do the same, right? Here, and then all of a sudden now I'm down here. I never hit 0, okay? So intermediate value theorem only works when you're continuous. That's important to know. Okay, so let's look at this guy. If I go from positive to negative or negative to positive on this interval, then I know there's some x value that'll make this statement true. I won't know what the x value is, yes, but knowing that there is one is also important. More important than knowing what it is. So let's see, is it continuous? And when we ask ourselves if it's continuous, we say, are we dividing by 0 anywhere? No, we're not. And are we putting negatives into even radicals? No. And are we having anything to do with logs? No logs. So we are continuous. This is a polynomial. All polynomials are continuous. Okay, so let's see if this actually happens now on our interval from 2 to 3. Okay, so f of 2 is going to equal 2 minus 1 to the 4th plus 2 minus 4. Okay, so 2 minus 1 to the 4th is just, or 2 minus 1 is 1 to the 4th is still 1, right? Plus 2 minus 4 gives you a negative number. What the number is doesn't matter, right? All I need to know is that it is negative. All right, let's try f of 3. Okay, so f of 3, if I plug in 3, I now have 3 minus 1 to the 4th plus 3 minus 4. Okay, so if I have 3 minus 1, that is 2. 2 to the 4th is 16, always, right? Because 2 to the 3rd is 8 times 2 is 16. So 2 to the 4th, 16 plus 3 minus 4, definitely a positive number. Okay, so I went from a negative to positive, right? And I had no discontinuities in between. That means that this guarantees a solution. So yes, solution exists. All right, so now we are looking at part B of number 15. So we're still using intermediate value theorem, and we're trying to determine if we know that there is an x value that will give us 0 on this interval. Okay, so as I said in the last video, intermediate value theorem doesn't work if I have a discontinuity, right? So once again, if I'm looking at this graph, and I have a function that does, one of these, then I know, hey, intermediate value theorem works from that point to that point, right? Because I went from, well, assuming that's not an asymptote, right? So I went from a negative to a positive. I had to hit 0. But if I'm discontinuous, it's no longer true, because if I have an asymptote that does this from this point to this point, right? I had a positive y value, and then I had a negative y value. So you'd think, hey, I must have hit 0 somewhere. But if I have an asymptote, it gets around that, right? Because it never touched 0. That's why we look for these before we use intermediate value theorem. So for this problem, tan x equals 0, you might be able to do intermediate value theorem, but you have to look really hard at your interval. Okay? So tangent, we remember that tan is sine over cosine, and it has asymptotes on its graph at pi over 2 and negative pi over 2, right? And plus pi from there. So at pi over 2, we are in between these two endpoints. That means we literally have something along the lines of this going on. Okay? Technically, graph of tangent looks like that. These are asymptotes. And it keeps going and going and going. So if you ignore the fact that it has an asymptote, you're going to get a wrong answer. Because you will have a positive number and a negative number, and you're going to think, hey, definitely have a 0 by intermediate value theorem, but you're ignoring this asymptote. So because of this asymptote at pi over 2, this does not guarantee a solution by intermediate value theorem. No solution by intermediate value. All right, now we are looking at 15, part C. Okay, so still looking with intermediate value theorem to determine if we can find solutions of, now it's this function on this interval. So, first step, right, is intermediate value theorem tells us if we have solutions, if we have zeros, right? If I can plug in an x and get a 0, because positive to negative or negative to positive, I know it hits 0. I don't know if it hits any other number. Only thing I know about is 0. So with this guy, it's not equal to 0. I'm going to make it equal to 0. Okay? So I'll solve it. I'll get cube root of x minus 2 minus 3 plus x equals 0. So really, this is the function I want to be thinking about with intermediate value theorem, because it's equal to 0. So essentially, can I plug an x in to get 0? That's what I want to find out. Okay, so next I'm going to be thinking about discontinuities, right, on this interval. So when can something be discontinuous? You might be tempted to say, this inside cannot be negative. And that's understandable because with square roots and fourth roots and sixth roots, it can't be negative on the inside. But this is a cube root. This is an odd radical, right? So because it's odd, the cube root of -1 is still -1. That's okay. Acceptable. So this can be negative. So this is always defined. There's no discontinuities in this function. So let's try plugging in our numbers then. So f of -2 is going to equal cube root of, plugging in -2, we get -2 minus 2 minus 3 minus 2. Okay, so cube root of -4 minus 3 minus 2. Now you might say that is going to be really hard to solve. But it's actually not, because I know the cube root of -4 is going to be negative. It'll be some nasty number, but it will definitely be negative, because that's a negative, just like cube root of any negative number is going to give you a negative answer. So negative, 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 minus a number, minus a number, it's going to give you a negative answer. Okay? I don't know what it'll be. It'll be some ugly number, but it'll definitely be a negative, and that's the only thing I actually care about for intermediate value theorem. Let's try -1. So cube root of -1 minus 2 minus 3 minus 1. So once again, we're in the same scenario where we have cube root of a negative, negative, cube root of a negative, minus a number, minus a number. This is also going to give you a negative. Okay, so intermediate value theorem doesn't guarantee you a solution. Okay, so what might have happened is we might be looking at a function that does one of these. Okay, so I plug in this point and I get a negative number, and I plug in this point and I get a negative number, but there's still solutions for when I hit 0, right? I can still plug in x values and make my y value 0. But it could have also been a function that looks like this. Okay, and I plugged in this number and I got a negative, and this number and I got a negative. So I don't know. I don't know if there are solutions. But I do know that by intermediate value theorem, it doesn't guarantee me any solutions. So no guaranteed solutions by intermediate value theorem. And this would be my answer.
The Teaching Center, UF's Learning Resource Center.